again. And let me take a picture of a picture. All right. These problems are what I call symbol problems.
Right.
That's not a real mathematical symbol. It's just a symbol they made up. And the
Yes.
symbol means is that whatever is on the left side of the symbol, you put in for x. Whatever's on the right side of the symbol, you put in for y. It's as simple as that. Okay?
So what are you saying is the left's, oh.
It's whatever's on the left of the symbol. In other words, let's start there, because you always start from the
Oh, now I get it.
yeah. And
so,
in other words, they're telling you that x pound y is this.
right.
Okay, and now you want x pound that. And so that goes on the left side of the answer. And it goes wherever you have x, right there. And so you get to this point down here where when you do x pound, remember that's x pound y, it's equal to whatever's on the left, x goes there, whatever's on the left goes there, and wherever we find y, you put it in where y is. Okay, so do you see how we get from here to here? That's the key part.
Well, that's what confused me was that second section where you have the two X's. I didn't understand how they got that part.
Okay. What this means is that whatever is on the left side of my pound sign, I'm going to substitute wherever I see x. Okay? That's why I substituted it right there. And it's going to immediately multiply x minus y. And so I see x again, so I put another x minus y. I took a picture of this so I wouldn't forget how to do it, because I got confused the first time I looked at it also. Now let me think about it for a moment. Okay, so it's all I did from here to here is just distribute.
Is it a way to, can you make that screen bigger because it's not bigger on my side?
Yeah, I probably can. Does that help? Yeah.
Oh, much better.
Good, yeah. All right, let me see if I can rethink my logic here. Pretty sure I got the right answer, but so this means this. We clear on that?
Yes, I understood that.
Okay.
And I understood the x squared minus xy.
Okay, good. In other words, is all I've done is distribute from there. So now we're taking x pound something that's on the right side. And according to that definition, the x, this thing on the left side, goes wherever we see x. And the y on the right side of the pound sign goes wherever we see y. Well, that's y, correct?
Yes, that's y.
So for x, I'm going to substitute wherever I see x. I see an x there. I see an x there. And remembering, I'm minusing an xy, so I'm going to have...
So wait a minute. I'm sorry. I'm still confused. When you say you see an x there and an x there, where are you getting those x's from?
All right, I may have actually made a mistake here. The more I look at it, let me go back and we're going to erase this. Oh, which it won't let me do. All right, let me go back to this beginning just so that
Sorry.
No problem at all. Trying to think what I did here. I think I have to go back to your original picture. Hold on a second. Let me get rid of that. That's the second part. The first part would be your first email. That's this one here. All right, let's start from scratch here. Maybe I did this wrong. All right, let me blow it up. And you can see that okay?
Yes.
All right, so let's try it again here. So this means, well, first of all, we work from the inside out. So it's clear that this is what that means. Because all I'm doing is substituting. It tells me that x pound y is equal to that. So x pound y is equal to that. And now I have x pound that quantity.
Right.
Okay? And the definition of what pound means is whatever's on the left side gets substituted for x, whatever's on the right side gets substituted for y. What?
Can you indicate left side and right side by different colors or something?
There's the left side, there's the right side. That's what I mean.
But
whatever's
that's the formula.
On the left side of the pound is going to go in right there and right there. So if let's use some numbers. Let's say I said, I'm going to go to way down here. If I said 2 pound y, that would mean 2 times 2, excuse me, I was going to use 2 and 3. If I said 2 pound 3, then it would be 2 times 2 minus 3. That's what that would mean. In other words,
okay, yes, I understand that. I understand that from the way the formula is set up at the top, but when you have x pound and then x pound y, I get confused as what's left and what's right.
It can be definitely confusing. So we're going to assume all of that is y.
Okay.
That's not y, but that's the right side, which means whenever I run into y, I'm going to plug that in.
Right.
Okay. Well, first thing I run into going through that definition of this function is an x. So the only thing I plug in is what's to the left of the pound sign. So this whole thing is equal to x times x minus, and now what do I plug in for y? The whole right side. That's the whole right side. So I'm going to put some extra parentheses. Okay, hold on. Let me work because I need to. Now is all we got to do is simplify that.
But before you get to that part, I understand the whole x times x minus y to substitute for y part. But the x, oh, okay, I see now. You're still using the same formula that's up there?
Exactly.
Oh, okay.
What this means is whatever's on the left side of the pound sign goes in for x. Whatever's on the right side goes in for y. So this is on the left side. This is on the right side. So substitute that for x, substitute that for y.
So x stays x no matter what.
Yes. Well, no.
Except if I were
to substitute numbers for this, it would be different. In other words, they could have said, what is 3 pound, 4 pound, 5? That would have been the same as what they've kind of said.
Right.
Okay, and now to figure out, we'd figure out that first, and that would be 4 times 4 minus 5, which is
Okay.
minus 4. So now this problem becomes 3 pound minus 4. And now
Okay.
whatever's on the left goes in for x. So that would equal 3
Okay, that makes sense now.
times
Okay.
3 minus y, which is a minus 4. And then you simplify that. 3 times
Okay.
7 is 20.
Thank you for clarifying. That makes more sense.
Yeah, well, I just realized that using numbers actually made it easier to understand. Because when you use their x's and y's, you end up looking at 4 x's there. And that's very confusing. Yeah.
Yes.
Yeah. All right, but anyway, the answer, pretty sure was that. No, maybe it was that. Well, let's see.
Well, show me how you
Okay, let's simplify.
worked it out.
Yeah, it's easy. Now, in other words, what we're looking at there is the answer. Just needs to be simplified.
Exactly.
Again, let's go from the inside out. So it's x times x minus, let's do that. That's x squared minus xy. With me?
Yes.
Still going from the inside out. So we got x times x minus x squared plus xy. Keep distributing. You have x squared minus x cubed plus x squared y. There's our answer. The last one, E.
Okay. That makes sense.
Normally, I would say these are easy problems because there's never really any difference in any of them. They can use whatever symbol they want. They can use a picture of an elephant instead of the pound sign. The whole thing to remember is that this concept of whatever is on the left side of that pound sign is substituted for x, whatever's on the right side is substituted for y. And no matter how many different nests they have, this is a nested one because it's x pound and then in parentheses x pound y. So you have to figure out that first. Well, they tell you what that is. And now it's x pound this.
Right.
All right.
Okay.
I guess that's this image here. All right, so we want to go to here now, right?
I think I gave you numbers 6 through 13 in a recent email because we finished at number 5. Oh, we didn't do 3 and 4, did we?
But it's from, well, let me look and see. We've done,
I don't think
definitely
we did
3. No,
we did do 3?
Yeah, because remember 3 is a problem where you kind of have to do it by long division because if you use a calculator.
Oh, that's right. We did do that one. Okay.
And you want
so
it as a number.
I think we're on problem 6, and I sent you that just a few minutes ago.
This is a big long file. Yeah, I've got it. This is the PDF file that has all of them, I think. Yeah.
Does it?
Yeah. Oh, yeah, because 5, well, I don't know if it does or not, but I got a long ways to scroll down here. Yeah, 5 is the one that gave me a little trouble because I was cross-multiplying my A with my C, and I needed to be multiplying the A with the C from the same circle.
Right.
I don't know why I did that, but I did. All right, so this is where we're going to pick up. Does that say the absolute value of x is equal to 6?
Good question. Yes.
Sign or a minus sign?
That's an equal sign.
Okay. So y Let me think for a second here. This might be a problem where we can answer quite simply without doing the algebra. Pick a negative number and a positive number and make sure that that number is above 10. Because 10 minus 6 is 4, and that could be critical. So let's pick plus 11 and minus 11. So when x, hold on, I got to take a snapshot, sorry.
But it says the absolute value of x equals 6.
Oh, again, I was thinking it was a negative sign. Okay. Which means that x can be either plus 6 or minus 6.
Right.
That's the only two choices.
So y can be bigger or smaller than 10.
Well, y can be 10 at max or smaller. And yes.
I mean 10 or smaller, right?
Yeah. Yeah, because if it's minus 6, then y is minus 2. So y can either be 10 or minus 2. So you can't tell how it compares to quantity b.
So it's D.
Yeah.
So one of the varsity tutor questions was the area of a sphere. I haven't seen that anywhere else. We can do that later.
Well, it's 4/3 pi r cubed.
4/3 pi r cubed. Let me write that down.
Don't know of a good way to really memorize that other than you know that it's volume, so your units have to be cubic units. So you know it's not going to be r squared because that would give you square units. So you know it's always r cubed. It's like a circle is pi r squared. This is pi r cubed. If you can remember the 4/3, that's the area of a sphere.
Okay. Thank you.
This looks like it could be a tough problem. Let's see. Just looks like it might be. Let me read it. The area of the ribbon is equal to the area of the base of the cylinder. So, what's the area of the base of the cylinder?
Is that where the N is? Is that what they're saying the base is?
Yeah, what's the area of that? Two-dimensional. It's a circle.
So that would be pi n squared, right?
Uh-huh. Okay. Now the area of that ribbon, if you unfold that ribbon, what will its width be? It'll look like that, will it not?
Yeah.
Okay, that's x. What is its height?
The circumference.
Which is?
2 pi r?
Or in this case, 2 pi n. Correct?
Yeah.
Okay. Therefore, the area of the ribbon, this is the area of the base. The area of the ribbon is 2 pi x times n.
2 pi
It's the area of that
x?
It's the area of that rectangle. It's the width times the height.
But wouldn't it be 2 pi n times x?
Both of them are variables. Doesn't matter. You can put them in either order.
So you wrote 2 pi xn, right?
Yeah. I could have written 2.
Not 2 pi.
I
was confused because I thought you had written 2 pi times n. That was my confusion.
Well, I had. This is 2 pi n times x. So that's the area of the ribbon.
Oh. Okay.
Okay. Now, hold on. See if I can figure out how to do this quickly. Now I'm going to have to write all that again. That's okay. In other words, what I was missing was, what was the relationship? Is it x or n? Okay, so let me rewrite that stuff here. I couldn't see what it was asking you to measure. And I can't scroll down without erasing everything that I had. So let's try again. The area of the base is pi n squared. The area of the ribbon is 2 pi n times x. And it wants the area of the ribbon is equal to the area of the base. So I now can say pi n squared equals 2 pi nx, correct?
Okay, hold on. The area of the ribbon is equal to the area of the base. So pi n squared equals 2. Yes.
Okay.
That's correct.
Now I can cancel that and cancel that and cancel the n with one of the exponents. So I have n equals 2x.
So n is bigger.
Always.
Huh.
Particularly if you can't use a negative number. In other words, if I could use negative numbers and I could let x equal -3, well then n would be -6 and it wouldn't be bigger. It would be smaller. But when you're using objects, dimensions have to be positive. There's no such thing as a negative dimension. So x has to be a positive number, so does n. And as long as they're both positive, then I can use fractions and it won't matter. N will always be greater than x.
So, okay. What if x were wider?
Would
it still work that way?
Wouldn't matter, yeah.
Really?
Well, make x as big a number as you want. Make x 100. N is 200.
Oh, okay. I see.
As long as n is 2 times x, then n is bigger, as long as we're only talking about positive numbers. Like I said, if you talk about negative numbers, then x would be bigger. -2 is bigger than, or -3 is bigger than -6.
Okay.
Okay. All right. That problem is a little, I mean, you were good to know the height of that ribbon. Not everybody, that's a tough one in geometry. Figuring out the surface area of something that wraps a cylinder. And believe it or not, that's a critical question for calculus also, is you have to be able to take surface areas and figure them out based on the fact that that unwraps to a rectangle. And the height of that rectangle is 2 pi r, the circumference of the cylinder. So that's definitely a good thing to remember. Although I don't know how many times they'll quiz you on that, but that's one of the more advanced ones. All right, let's see. I'm going to make us sort these, or do we have to sort them? Probably. Sometimes you don't always have to sort them, but most of the time, in fact, I can't remember one where we didn't have to sort. Which is unfortunate because it takes time, especially when there's a long list of numbers, and it's easy to omit one. So the way I always check is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I didn't miss any. What's X? Ooh. Okay, let's evens. Even. What's the median of the even numbers?
It would be between 2 and 6.
4. What's the, exactly between 2 and 6, yes. What's the median of the prime numbers? So that's prime, that's prime, that's prime, that's prime, that's not, that's prime, that's not, that's prime, and that isn't. So we have 6 prime numbers. What's the median?
Let's see. 1, 2, 3, between 3 and 5, also 4, right?
Okay, yeah. You're good with prime numbers? You know your problem figuring out whether a number's prime starts at 2?
Yeah.
2 is the
I think I'm good.
number that's prime. Every other prime number is odd, but 2 is strange. Right. But still 2 can only be divided by 1 and itself, so that makes it prime. Of course, 1 can only be divided by 1 and itself, and it's not prime. So I never quite have understood that, but
yeah.
Okay, and Z is the median of the least and greatest numbers in the list. Well, there's the least, there's the greatest. What's the median?
They're always even numbers, aren't they? So 1, 2.
Add the 2 and divide 10. By 2. The easy way to get all of these 3 answers is to add the 2 numbers and divide by 2. In other words, 2 plus 6 divided by 2 is 4. 3 plus 5 divided by 2 is 4. 1 plus 15 is 16. Divided by 2 is 8.
But wait a minute. How can it be?
There's only there's only 2 numbers in this list of Z. The list of the least.
Oh.
The least
it's not
is
the
1,
whole list.
the greatest is 15.
Okay.
Yeah, it probably would have been a little clearer if they'd have put parentheses around that. Because you're right, it's too easy to interpret that, which is what I think you probably did. In other words, you did the median of the least. Well, that doesn't have any meaning, actually. So you put parentheses around what you want the median of. Well, the least and the greatest numbers, that's 1 and 15. What's the median of that? 8.
Okay.
Okay.
Wait, where did you get 15? That's 13.
The 15 over here, do you not see that? You don't see that. Wow.
Yes, but 15, oh, right.
No, I'm just wondering.
I do see it on your screen, but I saw the 13th.
Okay, good. I was going to say, if you don't see it,
I can see it on the screen.
Right side of my screen. I've always assumed you see the right side of it. But maybe.
I can. I just didn't see the order of everything down there.
Okay. So now we have the median of 2x, which is 4. Excuse me, that's 8. Correct? X is 4.
Is 4, so 2x is 4, yes.
Okay, y is 4, and z is 8. So if you want, you got to order these. Let's put them in order. 4, 8, 8. What's the median of 4, 8, 8?
It's 8.
Okay. So that's 8. Z is 8. They are the same.
They're equal.
Mm-hmm.
Wow, that was confusing.
That was definitely different. Yeah, it was definitely different. Yeah, I guess the reason that you need to, in your head, put parentheses around this, because that really doesn't have any meaning. The median of the least. The least indicates 1.
Yeah.
You don't have a median of 1. If you have one
No.
item in a data set, you don't even talk about medians. So that's why you have to combine least and greatest and then take the median of that list.
Mm-hmm.
All right. Well, they always go in the same order, don't they? They give you 8 comparisons, and they give you one that requires you to enter a number. It's strange because this is Princeton Review, right?
It is.
They seem to use the same format. This must be the exact format you run into on the test. So what do I need to do here?
So oil is pumped from a well at a rate of 500 gallons per hour. So my tendency is to see, well, we already know how many per hour.
This is pretty
How many
straightforward.
gallons are pumped?
This is pretty straightforward. If I said
So it'd be 500,
gallons are pumped
500 times 3, 500 times 3.25?
Yep. That's the only difficulty at all, is converting that to a decimal of hours.
I had to report my hours for my observations this past semester, and I used Excel, and I figured out everything so that I can calculate.
You had to do that a lot. Yeah. So I don't know. Use your calculator to come up with that, I guess. What is that?
1,625 gallons.
Yeah, 1625. Okay. Click on the answer box and type in a number. Okay. I guess the only difference is most of the problems we've been seeing like that, you end up with fractions, right?
Right.
Which are particularly difficult if you're relying on a calculator, because calculator usually gives you decimals. Well,
right.
It always does, the one you'll be using. Some calculators will have a key on there that'll translate a decimal answer to a fraction for you, which would be particularly useful for this exam. But the one you're going to be using doesn't have that key. All right. Perfect question for a certain type solution. We can do this algebraically, we can do it back solving, or we can do it pick numbers and back solve.
Okay.
What are we going to do? Which one?
Okay, I'm still reading it. If the total number of pets the store sold in March and April combined was 500, how many dogs did the store sell in March?
This is what is key to knowing it's back solving. Because I can take an answer and I can plug it in the very start. In other words, if I pick 100, then I know that I sold 100 dogs and I sold twice as many dogs as cats, so I had to sell 50 cats. And I can then proceed through the entire problem and see if I get 500. And if I did, I picked the right number. If I didn't, I'll know whether I need smaller or bigger. And I can.
Okay, let's do that then.
Okay. So let's start with 100. That's a nice round number. That's an easier number to work with than 160, I think.
Yes.
So the math should be the easiest with 100. We definitely don't start with 80. Okay, so let's list it. If we sold 100 dogs in March, How many cats did we sell?
100 dogs, you would have sold 50 cats.
Okay. That's March. In April, the store sold twice the number of dogs it sold in March. So how many dogs did it sell in April?
200 dogs.
And 3 times the number of cats.
150.
If the total number of pets the store sold in both months was 500, bingo. Be amazed at how often B is the correct answer. And I think that's more than just coincidence. I really do. I think they intentionally make B the correct answer for people who are doing the problem correctly. Back solving is definitely the way to do it correctly. Notice that had these 4 numbers totaled less than 500, I would also know the answer. It would have to be 80.
Right.
So if either B is correct or...
Wait a minute. If those totals were less than 500, then wouldn't you have to go for a higher number?
No. Let's do 80. In fact, I'll do it in reverse. We'll start with 80 just for illustration purposes. So that's 80 and 40. That's 160 and 120. Add those, that's 240 and 160, that's 400. And we needed to sell 500. So 80 was not a big enough starting number.
Yeah, but you said that if the numbers we had done were less than 500, then we would have gone to 80.
Right.
Excuse me, I'm saying, wouldn't you have gone higher?
I said it backwards. You're absolutely right. I did say it backwards.
Okay, just making sure.
Yeah, if the numbers we had come up with were greater than 500, then I knew that the starting number would have had to have been smaller and we would know our answer without doing the math.
Okay, just making sure.
Yeah, and if I started with too low of a number, then we're going to come up with less than 500. So it's very clear here, despite my mistake, but it's very clear that you'll know which direction to go. And whenever that is the case, back solving, I've never seen a situation where it wasn't the most efficient way to go. Now, sometimes if you can't figure out which direction to go, well, then back solving might take you 4 attempts. You could try all 4 attempts and have to go with the 5th one. And that can take time to do the tabulations. So it's particularly valuable if it appears like it's going to be something you're going to be able to tell the direction of that you have to go, and this definitely looks like that. Because everything's based on March, the beginning, and they ask how many dogs did the store sell in March. Now, if this said April, that'll make all the difference in the world. And here's why. If their question said how many dogs did they sell in April, well, now you can't start at the beginning with this number. So it's not as easy to take one of these answers and work through the problem. You could still kind of do it because you knew that whatever they sold in April, they sold half that many in March. But it would be a slightly more complicated problem and it still lends itself to back solving, but not as much. The key on back solving is if the question they ask can be plugged in from the beginning of the paragraph and work through it sentence by sentence, and we were able to there.
Okay.
Whereas if they'd have said, how many did it sell in April? Well, then we got to start in the middle of the paragraph and then work our way back to March and figure out how many did they sell in March and how many cats were in March. You'd still be able to do it. It would just be backwards and then forwards.
Right.
but a perfect back solving. That would be in the dictionary of problems that work for back solving or work well with back solving. All right. Well, even though I hate to take the time to draw and label the rectangle, might be able to do enough of it to come up with the answer. Probably not, because it's asking about the diagonal, but so the vertices are -2, -1. That's W. The next one is -2y. We'll put it up there. That's X. And you can immediately tell that one dimension of this rectangle is y plus 1.
Correct.
Not sure that helps at the moment. Okay, the other dimension is 4y, which is right there. Now we know what we're going to be looking at here. In other words, now we know both dimensions. We know that dimension, which is 4 plus 2. Let's just label it 4 plus 2, that's 6. And we know, we might have, if we put the fourth one on there, we will be able to figure out that dimension. That's 4 comma minus 1. So this distance is y plus 1. This distance over here is y plus 1. That's comforting. That's 6. That's 6. The area of the rectangle is 18. Sometimes I forget to read part of the problem and I try to solve it without all of the information. And I'm seeing nothing but numbers over here. And when I'm looking at this, I'm seeing, well, it's 6 times y plus 1. The area of the rectangle is 6 times y plus 1, base times height. First of all, you see where I got y plus 1 and not y minus 1?
Yes.
It's y minus a minus 1. So it's y plus 1. Okay, so since they told us the area is 18, I can actually solve for y. Y plus 1 equals 3, y equals 2. So that is 3, that is 3. We now have a 3 by 6 rectangle. Solve that right triangle for the hypotenuse. In other words, this is what we're looking at. We're looking at a 3 by 6. Remember I said you're going to have to solve a lot of right triangles? This is just solving a right triangle. So
I remember you saying that, but I don't remember that it was a specific, well, obviously it's going to be 3 square root something.
Well,
and I think it was,
let's talk about solving right triangles, because I'm still convinced that it makes sense to do it the quick and easy way and not the hard way. In other words, I know you know the Pythagorean theorem. So
yes.
You can always go back to the Pythagorean theorem as your starting spot. Okay?
Okay.
But if I did that, I would say the diagonal squared is equal to 3 squared plus 6 squared, which makes the diagonal squared equal to 9 plus 36, 45, which makes D equal to the square root of 45, which is the square root of 9 times the square root of 5, which is 3 times root 5. So there's my answer. However,
okay, so the d squared is
that's
the diagonal?
The Pythagorean theorem. The hypotenuse squared
A squared plus b squared
the sum of the sides squared.
Right.
But what that means, and this is where I usually start when I'm solving right triangles, is the hypotenuse, let's call it that instead of the diagonal, the hypotenuse is always the square root of the others. So this is where I start, and I recommend all my students start. Rather than, all of them generally know the Pythagorean theorem, but if you go all the way back to that, it's easy to make a mistake, and it doesn't get to the immediate solution, whereas this does. If you start from the hypotenuse is the square root of 3 squared plus 6 squared, you get to here immediately, and then you can simplify it to there in one step.
The square root of 9 plus 36?
Which is 45.
Oh, it's 45, right, okay.
But let's talk about how we do any side of a right triangle. Call that A, call that B, call that C. So what we're saying is the hypotenuse is always the square root of A squared plus B squared. Well, what is A? A is always the square root of C squared minus B squared, and B is always the square root of C squared minus A squared. So the first thing to remember is that your answer is always square root of something. Always. Sometimes it's square root of 25, which turns into a whole number like 5, but not always. Usually your answer is a radical. So to remember these three, you really only have to remember 2. In other words, this is short side, regardless of whether A is the shortest side or not. If one of the short sides, that's always equal to the square root of the hypotenuse squared minus the other short side squared. So you don't need to really memorize that.
Right.
Just switch your A and your B. So the way to memorize this is when you're solving for the hypotenuse, it's added inside the other 2 variables, squared. When you're solving for one of the short sides, it's the hypotenuse first squared minus the other short side squared. So you're subtracting, hypotenuse always goes in front.
Okay.
This is the way I've memorized it, and it makes it quite easy to solve right triangles much quicker than normal. For example.
So any right triangle you could put that in.
I'm going to give you some right triangles. We'll make that 7, that 8. Give me the other side.
Okay. So the hypotenuse is 8. So x equals the square root of 8 squared. Forget whether it's plus or minus. Would that be minus?
Always minus when you're solving for one of the short sides. It's always plus when you're solving for the hypotenuse.
Okay.
So I know you know how to do that. So let me give you a different problem. Make that 4. Solve for the hypotenuse.
Okay, so x would equal the square root of 4 squared plus 7 squared?
Yes. The hypotenuse is the biggest side of that triangle. So you're going to have to be adding. Whoops.
So here's a question for you.
Put that plus or minus in there.
if you're doing this, if you're doing the square root of a square, wouldn't it be the same thing as x equals 4 plus 7?
No, not at all. Notice that this does not come out to be 11. This comes out to be the square root of 16 plus 49, which is 65. That's not 11.
Okay. I was just curious.
Well, notice that here's what you're saying. You're saying 4 squared plus 7 squared was equal to 4 plus 7 squared. Not
Which
a
is
true
not.
statement. Yeah, not a true statement.
Okay.
4 plus 7 squared is 121. This is 16 plus 49. This is 65.
Well, I guess what I was wondering is if you have a square root of something squared, wouldn't it just equal something?
Well, this is the most common mistake in algebra. What is the answer to that?
That would be x squared plus 1?
No. Not equal to that. You have to FOIL that. X
Oh, right. It's x plus 1 plus
plus
x plus 1.
x
Right.
plus 1 ends up being x squared plus 2x plus 1.
Plus
That's
1.
not the same as that. And yet,
Okay.
I swear to 90% of my students make that mistake. It is literally, I've read in math books that that's the most common mistake made in algebra. All right, let's see. What do we got? We got 10 minutes here. Oh, I love these. Actually, the reason I say that only partially kidding. In fact, I'm not kidding at all. Usually, these are different. You never run into this kind of a problem in a math class in high school. This is a GRE or GMAT special. Or LSAT. How many 3-digit integers can be created using only 5 distinct digits? Wow. I wasn't teasing. This is going to be hard. So let's take those 5 distinct digits. Think combinations. Every test they give you has a combination problem on it. We haven't seen a permutation problem yet, but we've seen a lot of combination problems. If you had to set this up as a combination, what would it be? It's N choose R. What are N and R going to be?
N is going to be 5, and R is going to be 3.
Correct. Now, remember the formula?
N factorial
over what?
Over N minus 1 factorial times R factorial.
It's actually N minus R factorial times R factorial.
Oh, what did I say?
You said N minus 1. The only reason, here's a good way to memorize this. There's 2 R's and 2 N's. And I could always remember that part of it, because that's the same as permutation. And then I couldn't remember whether this was an N factorial or an R factorial, until I finally saw that there has to be 2 R's and 2 N's. So this has to be R factorial. So this is 5 factorial divided by 2 factorial times 3 factorial. What is that number?
So, divided by 2 times 1, and 3, 2, 1. That would be 10?
Yep. The way to do that is to start there and make that 5 times 4 right off the get-go. Divided by 2. In other words, take the smaller factorial and wipe out everything to the right of that. So instead of 5 times 4 times 3 times 2 times 1, the 3 times 2 times 1 gets taken out by the 3 factorial on the bottom, leaving you with just 5 times 4 in the numerator.
Mm-hmm.
Okay? Now, I think that's the answer. One part of combinations and permutations that's always been difficult for me is figuring out whether something should be a combination or a permutation. Now, I assumed combination here because every problem we've had has been a combination. We haven't had a permutation problem yet. So I'm not sure they even give you permutation problems on the GRE. Seemed to me that how many 3-digit integers, well, order matters, doesn't it? In other words, that's not the same 3-digit integer as that. So if order matters, this would be 5 factorial over 2 factorial, which would be 5 times 4 times 3, which would be 60. And there would be more than fewer. Permutations, there's always more than fewer because this counts as one combination, it counts as 2 permutations.
So if it were a permutation, it would come out to 120, right?
I think 60. We would have 5 factorial over 2 factorial. In other words, it's just this part here. And 5 factorial over 2 factorial is 5 times 4 times 3, which is 60.
Oh, I see.
Wish it was 120. Because if it was 120, then I'd be certain that it's a combination problem. It feels like a permutation problem. Can you look it up? I think
Sure.
It's 60. I think the answer is 60.
Let's see.
The 1, 2, 3 is
That's number 12?
1, 3, 2. Huh?
I was just wondering what number it was.
12.
So let's see. This is section 5, number 12E, which is 60.
It is. So we've run into our first permutation problem. Now, as long as we know we're going to have both, then let's make sure you know the formulas. You know that one. And permutation is just without the second part of the denominator. In other words, permutation is this. And I suppose one way to distinguish whether it's a permutation problem or a combination problem is by doing exactly what I did. 1, 2, 3 is not the same as 1, 3, 2, but it uses the same 3 digits.
Yes.
So there's going to be more permutation problems. I can also have a 3, 2, 1. I can have a 2, 3, 1. Notice that I've got a lot more permutations than I got combinations.
Other way around, right?
One of those would probably have got 6 times. Yeah, I can probably find 2 more.
You meant more combinations than permutations.
3 digits. Yeah, I've got 3, 1, 2 and 2, 1, 3. There's the 6. So you can actually see that there are 6 times as many permutations as there are combinations. If I just wanted to know how many digits had the numbers 1, 2, and 3 in them, then this is 1. All 6 of those numbers have the digits 1, 2, and 3 in them. But if I wanted to know how many different 3-digit numbers can be created with those 3 numbers, that's a permutation problem, because this is different than this, which is different than that. In other words, if there's a difference, then it's permutation.
When order matters, it's a permutation.
When order matters, it's a permutation. If you're getting, and I can give you some examples that might be helpful, that have helped me. If you're ordering an ice cream sundae, and you can get 3 different types of ice cream, with your 3 scoops? Does order matter or not?
No.
No, because you're going to, I mean, some people might argue that chocolate on top, vanilla second, and strawberry third would be a different combination than vanilla, chocolate, and strawberry. But if you're thinking about eating a sundae, then you think of all of it's going to mix together anyway, so there's really no difference. In other words, if I go to Dairy Queen and I say I want 3 scoops, 1 chocolate, 1 vanilla, 1 strawberry, he shouldn't ask me what order I want them in. Although there would be people that would be a permutation problem. But when you run across that in a math book, it's a combination problem.
So one hint,
order doesn't matter.
One hint, I think, is when they say integers, you can think of it's on a number line, and those are different points on a number line.
Yes. Well, exactly. Very well. Yes. As opposed to letters, which wouldn't be as clear. In other words, would A, B, C, D be different than A, C, B? Not in combinations it wouldn't. In a permutation it would.
Right.
All right. That's a good one to stop at. We'll both remember that one because that's our first permutation problem. Actually, when are you retaking your test? Are we going to have it?
Tuesday.
Oh,
Tuesday.
This could be our last session.
Yeah.
Okay.
Can we do 13 quickly, or do you have a class?
Yeah, I can do 13.
Because that's the last one. Percent increase. Oh gosh.
Well, this is pretty easy. So let's start here. Let's answer that.
Okay.
He went from 5 million to 50 million. What's his percent increase?
That would be 10%, right?
10 times, which is 1,000%. Remember, 1,000%,
right. From 5 million
the decimal point over, 1,000% means 10 times.
Okay.
Okay. And what is the decrease that the workers went?
50%.
Right. $10 divided by what you start with. That's 50%. So the question is in terms of percent. It's not in terms of absolute amount at all. It's what percent greater than the percent decrease. Well, I would compare 100 or 1,000 to 50 and come up with 950.
Oh, okay. That wasn't so bad.
No.
Okay.
That's frequently the case. When you have a problem that's got that much wordage in it, it's usually not as tough as you think. That's almost key that it's an easy problem as opposed to a tough problem.
Great. Thank you so much.
You're welcome, Carolyn. Good luck. If I don't talk to you again, have a Merry Christmas and
thanks, you too.
Holidays, and good luck on your test.
Thank you.
All right.
Bye.